So in the last class, we have showed the way atoms are arranged in different crystal structures. And I have asked you not to see FCC crystal arrangement in the form of unit cell, cubic unit cell, but in the form of atom layers. All the atoms will be covered, only difference is how you look at them. So I look at them as there is an individual atom at bottom, it forms a layer, then there is a next layer, then there is a next layer, and the top corner atom is the part of another layer. So arrangement of layers in this way. Similarly, HCP, you look at the way the atoms are arranged in unit cell, the basal layer, on top the middle layer, on top again comes back the basal layer. And the slip occurs by mutual slide, by the slide of these alternate layers. In FCC, layers slide like this, in HCP, layers slide horizontally. This is how the atoms are arranged. So you please have a look again how the unit cell and how the atom arrangement looks like. Simple cubic, in a simple way you can arrange the atoms, and the unit cells are drawn inside the atom arrangement. Body centered cubic, the way atoms are arranged, if you convert them into 3D structure, you should look like this, where I am showing my pointer, body centered cubic, and at the right hand side face centered cubic, where the atoms are touching each other. In body centered also atom touching each other, face centered also atom touching each other. And if you arrange them, the structure looks in 3D in this fashion. But I prefer to look at them in a little different way, as how I prefer to look into them. I prefer to look at them like again and again. I am trying to show this, that this layer I see, this layer I see, so I see the structure as alternate layers of 1 1 1 plane, and when they slide, they slide. So this is one layer I am drawing, and this is the next layer, this is the next layer, and so on and so forth, and they slide with respect to each other. Similarly, as you are seeing the way I am drawing here, on the other side, you can, if you join the atoms, you will find the same thing. It's not just one set of 1 1 1 plane, but you can look in a different way also. So 1 1 1 is also, if you take this, if you take the other corner, or you may take this and you create a triangle, body diagonal triangle, then also that is 1 1 1 layer. So this is like 1 1 1 layer. Similarly, these are also 1 1 1 layers. These are also 1 1 1 layers. So that's why it's not a single family of 1 1 1. There are multiple family of 1 1 1, and for a particular set of planes, they are parallel, and when they slide with respect to one another. So I have covered a good amount of. So now let us move forward. As I said, don't look FCC as a cubic unit cell, but look like this. So here, one corner atom I see below, then one layer, another one layer, and the final corner atom. If one corner atom is one body diagonal position, another corner atom is the opposite body diagonal position. So here I find another corner atom. The body diagonal direction is basically 1 direction, which is perpendicular to the 1 planes. So the first is the red layer. If you arrange the red atoms, they form the red layer. On the groove of the red layer, you put B atoms as green layer. So this is second layer of 1. On top of B, there would be two options. Again and again, I'm saying, when you put B layer, you will find two options in B layer. Two sets of groups will be available. Which groups will be available? This is my question to you.
A and C.
Absolutely right. Absolutely right. On B, you will find two groups available, A and C. On any layer, you can arrange, when you arrange the next layer, you can arrange only one way, because you cannot arrange atoms, put atoms both A and C. They will dislodge each other. They will overlap. So either you have to choose A or you have to choose C. If you choose A, what will be the outcome? This is my question.
HCP.
HCP.
Absolutely right. Absolutely. On top of B layer, you will find A groups will again be available. Put atom CP. As simple as that. If you put atom in C positions, and on top of C layer, there will be two available, A and B. If you put B locally, what will happen? Suppose A, B, C. On top of C, you find two layer available, two position available, A and B. If you put in B, what will happen?
So the stacking sequence get disturbed.
Yes, stacking sequence gets
Stacking fault.
disturbed. And what stacking fault? And what kind of stacking fault? In FCC, when stacking fault occur, what is the atom arrangement in the stacking fault?
HCP type.
Absolutely right. Absolutely right. So stacking fault in FCC is HCP. So sometime when phase transformation occurs, when from austenite HCP martensite forms, it occurs by deformation. Deformation not only increases energy of austenite, increases MS temperature to MD, but also it creates nuclei for HCP martensite. There can be different type of phase. So stacking fault is basically an HCP structure, local HCP structure. Therefrom, a new phase can also form. So it's very important to remember that stacking fault in FCC is basically a HCP arrangement. Now I think you are picking up my point. Very good. So A layer, B layer, C layer. If you understand stacking sequence, everything is nice. I am arranging FCC oranges in the best packing condition, which is the FCC packing. I am indicating the 1 planes. So the plane in the basal plane is 1 Similarly, these angular planes are also 1 So the way you look, you can look, okay, one layer on top of other layer on top of other layer. I can look, okay, this is my first layer, this is my second layer. Next line is my third layer. Next line is my fourth layer. This line is my fifth layer. Similarly, I can take this layer and then this layer and then this layer, this layers. So basically, how you look, you will find the FCC and parallel planes. You will find parallel planes in FCC. So this is how again I am showing 1, 1, 1 direction. So the A layer atom I am showing. First body diagonal atom is A. You consider it as a layer. If you extend it, it will form a layer. On the group, there will be B. On the group of B, there will be C. On the group of C, you will find A is coming back. So you look along this direction. Along the AA direction, you see Burgers vector in FCC. Unit movement. What Burgers vector represent? Perfect unit dislocation movement. So to move an atom 1 unit, what you have to do? You have to push the corner atom to the face center to the next corner, right? So this represents a single unit perfect movement, and it is called perfect because it will reproduce your crystal structure. The slipped and unslipped region will have the same crystal structure, same translation. If it moves partially, then we call it partial movement. That can create stacking fault. But if it has a complete movement, then you will find B atom coming back to B position, and there will not be stacking fault. So this is a perfect dislocation movement. After I explain what is partial, you will appreciate that you understand now. And what is this movement? It's represented by Burgers vector B, which tells you the magnitude and direction of slip. What is the magnitude? A0 by √2. It's moving into A0 by 2, A0 by 2, 0. So Burgers vector is represented as A0 by 2. A0 is the lattice parameter. Initially 0, 0, 0 atom moving into half of 0 position. So Burgers vector A0 by 2, 1, 1, 0. And if you resolve it, its magnitude will come A0 by √2. And geometrically, if you calculate the corner atom moving into face center position, the real distance is A0 by √2. Under root A0 by 2 square plus A0 by 2 square. So A0 by √2 you will find.
Sir, can you repeat the perfect and partial distribution?
Yes. Here you understand. FCC layer you can see, FCC plane you can see. I am showing a 1, 1, 1 plane.
Yes, sir.
Yes. So let us consider the atoms are arranged on that plane. Okay. So let us consider this is my B plane. Okay. This is my B plane. Suppose there is a layer below that. So what is happening? When the corner atom moving into face center, what is happening? Is there any change in atom position?
Yes, sir.
Yes, atom position. But is there any change in sequence?
Yes, sir.
What change will be there in sequence? Stacking sequence, what change will be there?
No, sir. No change will be.
No change will be there, because if you consider the plane, the face center position is also B position, corner position is also B position. You understand? So basically it is moving from a B groove to the next B groove, which is called complete lattice translation. That means there will be a step formation, there will be a dislocation movement, but there will be no change in stacking sequence. Do you agree?
Yes, sir.
Yes, sir.
No need to agree. Don't agree if I am trying to explain a little more. There is a possibility. What is happening? There is a possibility. What else can happen? I will explain you in a minute what another possibility can be there. This corner atom moving into on the plane I have drawn. If the corner atom moves over here, that is a partial dislocation movement. Now will the stacking sequence change or not?
Yes, it is changed.
Now it is changed because on the plane that I have drawn, there should not be any atom at this position. And you know what is that position? Can anyone predict what is that position I am drawing?
Tetrahedral void.
No void. Very easy. So far, if you follow the discussion, you will be able to predict.
It is 1/4.
No, not that difficult. Not that difficult. No 1/4. What is 1/4? I have asked you not to.
B position.
I am not asking you to look into this unit cell wise. I am asking you to look into layer wise, right? So there is no 1/4, 1/3. I don't understand that.
It's the next word. It's the next
What
word.
is this position? Can you? What is that void?
C.
Hey, now you are, yes, that is the C void. The base center position on that layer, atom should be there. Corner position on that layer, atom should be there. But on that plane, in this particular arbitrary position, atom should not be there. But it can happen, this atom moves into this position. It may find it easy. If you apply stress, it may find it easy to go to here, and then after stress increases, from there to come back here. So the initial movement is your perfect movement because B moving to B without any change in stacking. But the next two movement I have shown is what?
Partial movement.
Partial movement, and it will create a stacking fault because it is changing the stacking sequence. But still, system can prefer to have the movement like this. So we call the perfect dislocation dissociating into two partial dislocations. It may happen when the system will find it energetically favorable. For this thing to happen, it has to be energetically favorable for the system. It may happen. and that is partial. Then the Burgers vector will be different. And if you join these two Burgers vector, you will find the original Burgers vector back. A0 by 2, 1, 1, 0. So A0 by 2, 1, 1, 0 movement can happen by dissociating into two dislocations. A0 by 6, 1, 1, 2.
So screen is not coming. The PPT is only coming that you are writing and it's not coming.
Sir, have you been drawing
The
something?
PPT is only coming, sir, right? Sir, PPT is only coming, sir. What you are writing is not coming. Yes.
My drawing is showing. I was I draw a sphere at a different location.
No, sir, that's why we are not able to follow. We have seen that slide only, Jan Burgers vector.
Yes, I am there only. I am there only. Okay, we will come back. We will come back. Don't worry. BCC 100 plane and the atom arrangement. Here you can see the slide. BCC.
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Pointer, laser pointer. You keep your questions. We will come back again. BCC not that close to pack. You can see atom arrangement is not that close to pack. BCC slip planes. You can see how the slip planes are 110, 112, and 123. And on that 111 direction is common direction. 111 direction is common direction. It lies on all systems, but 111 direction will remain constant. Whatever way slip happens, it can happen in different plane, but direction remains the same. BCC, Burgers vector, what will be the movement? For a perfect movement, can you tell? 110, 111 is the slip system. 110 plane which I am showing, and 111 is the slip direction. So how it will move?
In 111 direction.
What will be the one step movement?
So
First
body center, sir.
Body center. So corner coming to body center. And as the corner will come to body center, the body center will move to the next corner, right?
Yes.
Yeah, so that here you see FCC, what was the movement I have shown? Perfect movement. 111 plane, and what is this direction? For perfect movement, what is the direction?
110.
Absolutely right.
110.
Yes, so Burgers vector is having that direction. You see 110 direction is also seen. BCC, this is the movement. Can you tell me what will be the Burgers vector?
One.
A by 1.
A by 2,
A by-
1, 1.
By 2.
Let
A
us
by
see.
2, 1, 1.
Initially it was at 0, 0, 0, moving into A0 by 2, A0 by 2, A0 by 2. Burgers vector.
So your voice.
A0 by 2, 1, 1, 1. Voice is breaking.
Yes, sir.
Wait, hang on. Moving. Baba net করো না, হ্যাঁ? Is it better here?
Yes, sir.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yes, sir. Yes, sir.
Yes. So
Yes, sir, you are audible now.
you see, Burgers vector A0 by 2, 1, 1, 1. You have to consider the slip plane and slip direction. Slip plane is also right, 1, 1, 0. Slip direction is also right, 1, 1, 1. And Burgers vector movement means one perfect step movement. On that plane, on that direction, one atom moving into immediate next scheduled position, not any arbitrary position. Okay. HCP, basal plane arrangement we are showing, and the direction. What is the direction? What is the nearest neighbor direction? Can you tell? On the basal plane, what is the closest direction?
Sir, 1, 1, 2 bar 0.
Basically, can you express in words that from where to where atom has to go? If this is one perfect movement,
Sir, from the corner to the center of the basal plane.
absolutely right. You know that sleep occurs in the closest direction, right? So from any corner atom moving into the center of the basal plane, or center atom moving into any corner position, you can see the arrows, right? You can see the arrows drawn on the basal plane. There are 3 arrows, right? Double-headed arrows. Can you see the slide?
Yes, sir.
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Yeah. So one step movement along any of these 3 directions. One step movement along any of these 3 directions. And there is no rise in height, right? So 1, 1, 2 bar 0, that 0 is, there is no change in height. It's not moving upward. Movement is happening on the basal plane. Now why 1, 1, 2 bar? Why 1, 1, 2 bar? Slip direction is represented by 1, 1, 2 bar. Why is that? Previously we were discussing one day, right, in class?
Yes, sir. Yes,
The
sir.
closest
The
back,
axes are
sir,
like
no
that, no,
spacing.
sir.
Now I am drawing the basal plane here. Okay, look into this. I am drawing the HCP basal plane here. Okay, and this direction is L, height or length, which is 0 because there will be no movement on that direction. So this is 0. Now there is an obligation in HCP lattice Miller indices that it is represented by H, K, I, L, right? H, K, I, L. Where? What is I? What is I?
Minus of H plus K.
H plus K.
So this formula has to be maintained. This formula has to be maintained. Now, I am trying to show you a movement, okay? I am trying to show you a Burgers vector movement. Suppose I am bringing body center, not body center, face center, basal plane, face center atom from the center to corner position. This is a perfect movement. You agree or not?
Yes, sir.
You agree
Yes,
that
sir.
is the perfect movement. But I have the obligation to represent the direction in this way. So how I will represent this direction? Following this formula, L equal to 0. So that is now established, right? You agree to that?
Yes, sir.
Now see how I am moving that direction. What I will do now, to show this direction, I have to take a very complex path. What I do, along positive A1, I move one step. So from base, I come to the point A1. You agree? Can you understand? I move one step this side along A1. Now I have to move one step along A2 to come here. So again it is 1. You agree? 1, 1. So H
Yes.
equal to 1, K equal to 1. Automatically what I becomes?
-2.
-2.
-2. But positive direction of A3 is this side. So I have to now move -2 along A3. So I have to come 1, this point, and again 1, this point. So this movement is -2. You understand? So where I am now? I am now here. I am now here. You understand? But direction wise, I am right. Only I moved, I had to move one step. I move now 3 steps. You understand? So what would be my Burgers vector? I have to reduce the magnitude by dividing it into 3. So my Burgers vector I write A0 by 3. 1, 1, 2 bar 0. Now magnitude and Burgers vector wise, I am in the right point.
Why A0 by 3, sir?
Because if I am moving 1, 1, 2 bar 0, I come how many A0 I cross? I cross how many A0?
3.
3. So I have to divide it by 3. Because I am here. I am 3 steps away where my unit movement is only 1 step. Think about it. It's not very difficult. Only I have to maintain the Burgers vector, which represents the magnitude and direction of slip. In HCP, we know that slip occurs on the basal plane, and we know what are the Burgers vector. But also some other planes may come into play, like in BCC, more than one planes come into play. In HCP also,
So we are not able to hear you.
Hello.
am I audible?
Yes, sir. Now
Yes, sir.
you're audible.
Now, sir, you are audible.
Yeah, I was disconnected actually. They say that something went wrong. And we are trying to fix it, something like that they were saying in Teams. So I had to go out and I had to come back. My screen is shared? Okay. Okay. So you think about that, and that direction can also be represented by bar1 2, bar1 0. Only thing that formula has to be maintained. The direction should be right, and the magnitude should also be right. 1 unit movement, perfect unit movement. That's why HCP Miller indices is little more complicated. But if you think the way I have shown, it's not difficult. Again, the same things are shown. Preferred direction. Miller indices is written H plus K equal to minus I. And the Burgers vector is shown here. And the movement direction is also shown. FCC, I have told you that there are 12 slip systems. Depending on how you apply load with respect to your slip systems, 5 can easily get activated because minimum 5 slip systems required to deform by maintaining continuity. And HCP metals are most ductile because their 1-1-1 planes are very closed pack planes, and they are octahedral planes. I am again time and again repeating that the arrangement here of these planes are such that always you will find some plane or other is in a favorable position. and slip occurs along them. This calculation is shown here. In BCC, calculation is shown where from 48 slip systems will be coming, 6 independent 110 plane, and each plane contains 2 111 direction. So here from comes 6 into 2, 12, 24 independent 3 to 1 planes, non-parallel planes, each containing 1 111 direction. So here from comes 24, 12 112 planes, each with 1 111 direction. So here from comes 12. So 24 plus 12 equal to 48. And among them, 5 gets activated. No problem. So reasonably they are ductile, but less than FCC because the planar density is less. And often it happens that if not 110, other planes also come into play into slip. That's why more than one slip system participates, predominant slip system participates. So the slip is called wavy slip. In FCC, we find the slip steps that forming inside a grain is mostly parallel, because one set of slip system is good enough to take care of the entire deformation. But in BCC, multiple of them, 111, 110, 112, 123, all comes into play. So dislocations often move from one to other systems. So we call wavy slip. You will find the slip steps that form are wavy. In FCC, it's called planar slip, and BCC, it's called wavy slip because lines are often bent as if in a wave, and multiple things are coming into play. So cross slip becomes very important. That's why screw dislocation and cross slipping becomes very important in BCC. So screw dislocation, cross slip dictates plays a very important role. HCP, I have already shown. Generally, it is shown basal gives 3, but actually basal gives 2 independent. If you consider one basal plane contains 3 directions, as I have shown before, but actually out of these 3, 2 are independent, because movement in 2 can take care of the third because of the mutual relation between them. So pyramidal plane and prism plane, as I have shown, they contribute to 1 1 each, but overall total slip system remains 4: 2 basal, 1 pyramidal, 1 prismatic. So total number of maximum slip system is 4, but you need 5 to maintain continuity. So HCP material is not ductile. Slip is difficult in HCP materials. Zinc, cadmium, HCP magnesium. Deformation by slip is difficult. So what is the...
Sir, how there are 4? Can you explain, sir, once again?
Yes, actually basal contributes to 1 basal plane, right? 1 0 0 0 1 plane in 1 unit cell. How many? How many 0 0 0 1 plane in HCP unit cell?
2 planes.
2 planes. Out of that, how many we will consider as independent?
1.
1, because they are, the 2 are parallel, right? So they will slide when deformation will occur. That's why in FCC we have considered 4, whereas there are 8, 1, 1, 1. 8 corners, therefore 8, 1, 1, 1 in FCC. But independent slip, we have to consider those planes which are non-parallel. That's why we considered 4. And then we have to consider on any one of those planes how many slip direction lie, how many independent slip direction lie. On 1, 1, 1, 1 FCC, how many slip directions lie?
3.
3.
3.
Yes. So similarly, in HCP, how many slip directions lie? In HCP, on one basal plane, how many slip directions lie?
3.
3.
3, right. 3. Yes. Yes. So in general, in Ditter's book, you will find in HCP how many independent slip system is mentioned?
3.
3. Right. So let us not complicate the matter, because towards later stage we will try further understanding. Okay. So whatever I said, you keep in mind. For the time being, you remember only 3, which is less than 5. Okay. Later on, we will try to understand in a greater depth. I said something. With time, we will do further understanding. Let us leave the matter here, okay? But overall, it is less than 5, and therefore, what is the conclusion? What is the conclusion of the whole story that I told so far?
HCP is less than
Utility of HCP.
P is less, because there are, for slip to occur, maintaining continuity, 5 independent slip system is required, but HCP do not have 5. Therefore, what is the preferred mode of deformation in HCP?
Twinning.
Twinning. So in metal, predominantly, if someone asks you what is the preferred mode of deformation, what would be your answer? If someone asks you in metal, what is the predominant mode of deformation?
Slip.
What is the answer? Slip. Absolutely right. Absolutely right. So number 1 is slip. What is number 2?
Twinning.
Twinning.
When twinning will occur? Twinning requires when slip is restricted. In FCC, can twinning occur?
Yes, sir, it can.
When? When?
So when temperature is very low.
Height.
So one said low, one said high. Which answer is right?
Low.
Why low? Why low?
Because
At
slip
low
is
temperature,
predominant.
dislocation moment is
Yes,
difficult.
because at low temperature, dislocation movement is restricted. Very right. Very right. Similarly, if the strain rate is very high, then also dislocation movement will be difficult. In assignment, I have given those questions. Again, there can be possibility of twinning. The lady said, what is your name? Who said hi? Yes, who said hi? High temperature, high temperature. Please come forward. Don't worry, you just tell that I said hi.
So me, sir.
Very good. Can you explain? Who are you? What is your name?
The Soumya.
Soumya, now you tell me why you said hi. Don't get confused, okay? A lot of things are there and it's good to have a discussion. My answer is high is also not a bad answer. In high temperature also twinning can happen. Soma or any other person can want to tell?
The annealing twin occurs.
Right. So there are
Yes,
two
sir,
types
that's
of
why
twin.
I said.
Yeah. So you couldn't
In,
answer, Soma.
for example, like for additively deformed samples.
Anyway, I don't additive, I don't know. You should give the fundamental explanation that there are two types of twinning. One is deformation twinning. So what I am talking so far is the deformation twinning. And deformation twinning is restricted when sleep is restricted. Deformation twinning happens when sleep is restricted. But some systems, annealing twin is completely different. It's not related to deformation. It's how the new recrystallized region forms. If it is oriented in some way with respect to your parent crystal, in twin orientation, in mirror image kind of an orientation, it's called annealing twin. It's completely different from deformation twin. So what we are talking so far is deformation twinning. But what Soma said, high temperature that can happen is annealing twinning, and that is associated with recrystallization. Let us understand again stacking, atom stacking, atom stacking. A layer. On top of that, B and C layer. B grooves and C grooves. Whatever groove I choose, B or C, that doesn't matter if A layer is my first layer. The next layer I call B layer. So on A layer, sitting B layer. On B layer, there will be A and C grooves. If I put atom in C, then it's FCC. The way the atoms are arranged, you see here, and the planes I am showing also. These are the parallel planes. So when sliding occurs, on this plane sliding occurs. A layer, on top of that B layer, on top of that C layer, on top of that A layer, B layer, C layer, like that. Is the atom arrangement. This is stacking. This is stacking. Parallel 1, 1, 1 planes. Time and again I am trying to show parallel, 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 parallel. This is the way parallel planes look like in a body. Don't always look at 001, 010, tilt your image and see these parallel planes, A layer, B layer, C layer. A layer, B layer, C layer arranged in stacking. A layer, B layer, C layer stacking. If there is a change, then what is happening locally in the right hand side image, BC, BC. What has happened? A atom moved into B position. A atom moved into B position. So what has happened locally? What has happened?
HCP structure has found.
HCP structure, HCP stacking has come. So that means a stacking fault. This is HCP stacking. Okay, taking 5 minutes break. I'm coming back.
Sir, you are not audible.
Hello. Are you there?
Yes, sir.
Yes.
Okay. Yeah.
Yes, sir.
Let us start another exercise. Again, stacking. We will now understand partial dislocation and stacking fault. I have a request that when you visualize, because you now understand how the atom arrangements are, when you visualize, looking in this way is much better because you understand now very well. What I am showing in this atom arrangement, what kind of atom arrangement I am showing here? Can you tell? What is the phenomena happening?
Stacking.
Stacking, right? I am drawing A layer. Suppose I am drawing FCC 111 planes. So this is my A layer. On top of that, I am drawing B layer. And B atoms, where they are situated on A layer? On A layer, B atoms situated at which positions?
Grooves.
Absolutely right, groups. Groups. So in this arrangement, I am showing A layer on top, B layer atoms. A layer is in red on top, B layer atoms are situated on a set of groups. There were two sets of groups. But when you put atoms of same size, you have to choose one set of group. You cannot put atom in both the sets. Do you agree?
Yes, sir.
Yes, sir.
I cannot put the atom. I am drawing a group, right? If I put an atom in point number 1, position 1, can I, on the same plane, can I put an atom on the position I am showing by a spot?
No, sir.
No, because
No,
they
sir.
will knock out each other. Okay, they will knock out each other. I cannot put a atom. Now what I am applying is, I am applying on the B layer, I am applying a shear. As I am showing, I am applying a shear. So what B layer will do now on top of the A layer? It will now?
It will slide, sir.
It will slide. Absolute right words you are using. It will slide. So what is the perfect movement? If it slides, what is the perfect dislocation movement? Now you tell, what is a perfect unit movement? One Burgers vector movement. You tell.
Next group position, sir.
Can you tell a number?
1 to 2.
1, 2.
Absolutely right. 1 is going into 2. 2 is going into 3. Then someone is hanging in between or whatever, that will form a dislocation, and it continues then 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, and then a step will fall. 1 to 2. But 1 to 2 movement, there is a high energy barrier. Could you understand the difficulty associated with 1 to 2 movement? One to two movement is more difficult. It requires a high energy barrier to be crossed. Could you understand why? Could you understand why?
Yes, sir.
You tell why? Why there is a high energy barrier I need to cross?
Sir, you told in perfect lattice, we can correspond to that also. You told in that
Not that respect. Suppose I can movement is easy. Suppose movement is happening. Huh? In perfect, I am not coming into perfect or imperfect here. Suppose my movement is possible. You think physically, one layer of marble, on top you arranged another layer of marble. You are pushing top layer marble with respect to bottom layer. What will be the problem associated with that movement?
It will disturb the surrounding regions.
No, even more simple way you tell, even more simple way, look into this picture and tell. Look
Like
into
atom on
this. Yeah.
atom on
Yes.
atom.
Huh?
Atom on atom, it goes just atom to atom. So that's why.
Yeah, that has to happen. Atom to atom, the movement has to happen. But what is the problem in this movement? Huh?
Atom above atom. So
It
like
has to go up and come down then.
Absolutely right. That's what I want to point out. For 1 to 2, it has to go up like this and then come down like this in the groove. It is not a very easy task. You need higher force. So if you consider force and distance or energy or distance, whatever, force displacement is energy and displacement, suppose delta. So literally you push atoms like this. And that's why I asked you, look into this kind of model, because now you understand that atom number 1 is situated at a groove. It has to move to the position of atom number 2. So literally what it has to do? What it has to do? You tell? Huh? Crossover. Crossover. It has to, you have to push atom number 1 to lift it up on top of the atom number 0, and then it will drop. So for that you need a maximum stress, some stress you need, you understand? The energy barrier will be like this, the stress barrier will be there. But there is one easier way. Can you pick up the easier way?
Yes,
Sir,
sir,
it
the
can
black
go
dot.
to C group.
And then?
And then it can came
And then it come back
to which group?
To B group.
To B group 2 position.
Yes, sir, 2 position.
Isn't it fascinating? So what I am telling is, more easier option is for this atom to move along the groove. Along the groove, reach the C position. And accordingly, all these atoms will move like this. All the B atoms will move into C position. You understand? The entire set, instead of moving from B to B, moving into B to C. But since you are continuously applying pressure in this direction, when that stage is a metastable state. B atom in C position is not a stable state, it's a metastable state. It will come back to the more stable state, which is C to B, again moving along these grooves. So if you set a marble, put another layer of marble and put movement in this way, you will find there's a tendency that marble layer, instead of riding up the bottom layer and falling down, they are trying to move along the grooves.
Means one group to another.
Yes, one group to another. So from 1 to 2, it's moving along the groove to C position, because from B to C, it just need to move along the groove. And then gradually this movement is happening, that then it is coming back to again to B, because you are continuously applying stress. So the energy barrier now reduces to you understand? You have to apply certain force, certain stress to move it into C groove. This is your B1 group to C group, coming back to B2 group. But the energy level at C group is higher, because that creates a, if B layer atom moves to C, what will happen? C group, what will happen?
Stacking fault.
Stacking fault. Now let us see. This is my A layer. So this entire body is my below the slip plane. On top of that, B layer is sliding. On top of that, B layer with entire above layer is sliding. So in this process, if B atom move into C position is somewhere here shifted. You have to understand group wise. So they are not exactly on top, they are different. Huh? C group, and from C group it is coming. So if it happens that C position is occupied here, so if B atom goes to C position, naturally the above planes will move to the next group, because not this blue group is moving. Top C group will move, where C will now go. On the B
So
group,
not
there
got your point how
Yes.
stacking faults are created, so that you can show this what will be this pattern after the after
So if B layer goes into C position, what will happen? B layer on A layer, B layer is sliding, okay? B layer and all the top layers along with B are sliding. Now, what was the layer below A layer? According to the sequence, what was the layer that comes below A layer?
C.
Below that, there is a B layer. Below that, there is a layer. Very simply, I am telling that the part 1 is stationary, part 2 is moving. And the above part is, and the shearing is taking place between these two planes only. Okay, between A plane that I am mentioning and B plane. So this is my slip plane. Now, if B position atom moves into C position, what will happen? Where this C position atom will now go?
A position.
Where the A position atom will now go?
B position.
So locally, what is happening over this portion? What's wrong in this portion? I am drawing a 4 layer. I am drawing. Remaining problem is not there. Remaining will be restored.
HCP is getting.
Yes.
HCP pack.
CACA. That means AB kind of thing. Whether it's AB or BC, whether it's CA. Ultimately, over that, a fault is created. And why that fault is created? Because B atom, it's difficult for it to move from 1 to 2. Instead, it preferred to slide to group C. So all these B atoms of this layer in a particular portion will slide to group C. And if the slip is complete, that is the incomplete slip, that is called partial. And if the slip is complete, then from C again it's come back to the next B, because you are continuously pushing the B layer in this direction. So instead of moving from 1 to 2, it's moving like this, which we call, if this is my Burgers vector B1, this is my Burgers vector B2, and then coming back, which we call Burgers vector B3. So we call dissociation is taking place where B1 is dissociating into B2 plus B3. Dissociating means instead of this movement, the movement is happening by the combination of these two.
Means that to go to 2, it's first going to C and then going to 2.
Yes, exactly same. From B1, if I write it B1, and if I write it B2, from B1, it is going to C. That is called creating stacking fault, and it is coming back to B2. If you try, why not you try an experiment? You buy a set of tennis, maybe a lot of tennis balls would be required, but arrange tennis balls, put the top layer on the, put 2 layers and try to push them. You will find rather than jumping up over the bottom layer, the top layer is trying to slide through that groove. At a lower stress that will happen. Of course, it can happen. A complete movement can happen. But rather than that, ultimately comes which one is energetically favorable, easy, which one requires less stress. To some extent, could you understand what we are trying to tell?
Yes, sir.
Okay. A layer, on top I am drawing B layer. These are my B position. These are my B position, where if you put one atom, you will find out the position. So now you tell what is this position where I have put, or the point where I have put a star. I have located a point. What is this position?
C position.
isn't it? If this is my B, can I put another B here? Can you see my round that I have created on the canvas screen?
Yes, we can see.
Can I put another B there?
No, sir.
No, they will knock out. So that is not the B position. So what position is that? C position. This is the C position.
C position.
The group that remain vacant. Can I? Sorry, I again got disconnected. Can you see the canvas screen? Hello? Yes, yes.
Yes, sir. Yes, sir.
You understand what is this position? I can put a B ball here at this position where I have located it. Yes?
Yes, sir.
Yes.
Yes, sir.
I cannot put a ball here where I have located it.
No, sir.
Right. Yes. So now I am trying to expand the drawing. Okay. Now let us put a C atom in a different color. Okay. Let us put C atom now. Once you put, you understand which is C position. This may not be properly put. Automatically it will be decided. You put in one group, you will understand. So which locations now I am filling?
C location.
C groups I am filling. B. So you understand what I am showing here? No, possibly not right. Can you explain this drawing to me? What is happening? Can you tell?
So this is stacking fault.
This is the stacking fault. And I have shown my stress is in this direction. So I'm trying to push B layer on top of A layer, B and above layer. Don't think only A and B. Slip is happening between A and B, this layer which I have drawn, but B and it's all is above. B, C, A, B, C, A, B, C on top. The entire body on top of B. So the entire body is sliding on top of B, and the entire body below A is remaining stationary. So this is my A layer. On top of that sliding is B layer. And along with B layer, the entire top part is sliding along with. It's basically carrying. B layer is carrying all the above layers on his shoulder and moving. In this process, what has happened? B layer atoms moved into C position. So the sliding is taking place in this direction. So can you explain what is happening in this case? So what is this intermediate region? I'm drawing certain lines, right? I am drawing certain line. You look into these lines. And it's not necessarily that every point atom has to be there. There can be some vacancies also. So the line can be bent also. So what is the region between these two lines?
The ACNC stacking fault.
The stacking fault.
Stacking fault.
And what are these two lines?
Dislocation.
Partial dislocations.
Partial dislocation.
Partial dislocations. These two lines are basically the partial dislocations. What is this side of the structure? What this side of the structure is showing? As my slip direction is this. Can you tell? Things are happening in stages.
Before that line, it was a perfect dislocation. It splitted in the partial. Then again,
In this position, I would say perfect sleep has occurred. Perfect sleep has occurred. So I will call it slipped region, completely slipped region. So these atoms are back in B position. They went to some C position and then back in B position. So this we call slipped region. This is basically slipped region where perfect movement has taken place. B back to B. What is the intermediate position? Stacking fault, surrounded by what?
Partial dislocation.
Two partial dislocations. And
So
what
why
are
we called it as
Yes?
call it as partial dislocation? Why not it is a perfect dislocation?
No, because
Sir, by drawing the
yes, if it is
sir, by drawing the
perfect,
Burger circuit, sir can yes.
yes, if it is perfect, then there would not be any stacking fault. Partial means it has not gone into the unit movement, it has gone partial movement in a different direction, which created a incomplete translation. Translation means the bottom part will be exactly the same as the top part. But here it has created a fault. And partial because it is not incomplete. What is the complete dislocation? Complete dislocation is B atom to B atom movement is complete. If it moves into somewhere which is a metastable position and then come back, it's basically, I would say, the component of B1 dislocation. If perfect dislocation is B1, then the Burgers vector of 2, B2 and B3, these are partials, means these are part of B1, but it's not complete B1. So what word is perfect? Means if B1 is perfect or complete, what would be the right word for partial?
Imperfect.
Imperfect or incomplete. And Burgers vector 1 unit movement, if you can now calculate, I can ask you to calculate what is the movement necessary for B2, what is the movement necessary for B3. Now you can ask me, sir, this one is my position B, this one is my position B. Why had gone into this position and then come back here? It could have gone through groups here, here, here. Through groups, it could have moved like this, here, 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 here. This could have happened. Could you understand my point? Why it has to move by this movement plus this movement. If group movement has to happen, it could have moved into any other groups and then move into any other group, could have moved into any other group, move into any other group, could have moved into any other group.
The lowest energy is
exactly. So energy, ultimately it's energy that you have to understand. What I have told, don't consider it will happen always. It will happen if there is a condition. What is the condition? If energy of B1 Burgers vector movement is greater than energy of B2 plus B3 Burgers vector movement. That sets the criteria, isn't it? If the total energy of these two exceeds this, then what will happen? Then what will happen?
Directly
B will go to B. It's not necessary that B has to go to C. It's all the difficulty associated.
And sir, if it is equal both the sides, then which one will be
Yeah,
preferred?
then it is a critical condition. It's thermodynamic. You understand? Thermodynamics. So it's not like that, that something is equal or 1 point down, or means, yes, it has to 1 point down equal, then it will not happen. It has to be, the critical criteria has to be this equal and exceed, means, and it's not, even if this criteria is met, it's like thermodynamics. You cannot say that it will happen, because thermodynamics says something. But does that always happen, that phase transformation will occur? But do it always occur? Suppose something is thermodynamically valid, does it always happen?
No, sir. Kinetics also.
No. Yes. Yes. Sometimes we get austenite at room temperature. Do you think thermodynamically austenite is stable? In some conditions,
723.
but some condition things cannot change, because see, a body, heavily deformed body, do you think it is stable, thermodynamically stable?
No, sir.
No, because it contains a lot of defect, so it is not stable, it is unhappy. It wants to reduce its energy by eliminating the defect. But can it eliminate defect? No, because you have to heat it, so that necessary thermal activation has to be there in the form of diffusion, so that it can release its energy. Okay, so don't think that, first of all, don't think that always B atom has to move into C position, and then no, it may not happen. You may also consider, okay, I am taking a more crooked route. Instead of B2, B3, why I will take B2, B3? I take another route. I will take B4, B5, something else. B4, B5. Okay, boss. I will ask you, all possibility exist, but you have to check energetics. Energetically, which one is favorable, that one will actually happen. If energetically a perfect movement is favorable, then perfect dislocation will happen. If energetically a partial movement is favorable, then what will happen? Suppose your condition met. Suppose your energetic conditions met, that B2, B3 movement is energetically favorable than B1. Then it tells that, it confirms the feasibility. Then it tells that it can happen. If this condition is not met, then it will never happen. If thermodynamics is not met, nothing will happen. If thermodynamics is met, then it can happen. But can you say it will happen? This is my question to you.
Not always, sir.
Yeah.
No, sir.
Why not? Why not?
Theoretically correct it should be, sir.
Yes. This is what we were discussing today with Rakesh Barik, that if this condition is met, stacking fault, possibility is there. But whether it's a stable stacking fault or unstable, it may not happen. What will decide that? Can you tell? Can you
Some
tell?
velocity.
No. One more factor. One more factor that we are not considering here. What is that? Whenever I am creating
Free
two
energy, sir.
partial dislocations, there was one parent. Instead of parent, it's happening in two partial dislocations. These partial dislocations have a characteristic. What are these characteristics? They are basically same type of dislocations. Same type of dislocation. Now, if two same type of dislocation come together, what will happen?
Repel each other.
Repel each other. That is the right answer. They will repel each other. Like to, what to say? Yeah. So they will repel each other. But if they repel each other, then there is a problem. What will happen, you know? If they repel each other, their distance of separation will increase. My point is, whether these two partials will lie something like this, whether these two partials lie something like this, or whether two partials lie something like this, what decides?
Stacking fault energy.
You understand my point? What will be the width of this stacking fault region? Here I am showing a stacking fault region of this width W, say maximum width. You may have asked, sir, why not it has happened that up to this point perfect B slip, from here perfect B slip, and only a little stacking fault with another width W2? Why what chooses that this much will be the width of the stacking fault? Who said that?
Stacking fault energy.
Because you are creating a fault, it is associated with the energy. It is associated with the energy, stacking fault energy. And depending on the metal and alloy you are using, there is a certain value of stacking fault energy, which is represented in the formula like joule per unit area. So stacking fault energy unit is joule per meter square, say. Joule per meter square. Now if these two brothers want to repel, they are fighting, they want to move away. So what will keep them at a certain distance? If they move very much away, if the repulsion force creates a very large width, what will happen?
Large stacking
What will
fault
happen?
will be created.
The stacking fault energy will increase, or the total energy, because the total fault region is increasing. So if I consider gamma is the stacking fault energy per unit area in the form of joule by area, then gamma into W represents my total energy of the stacking fault region. Do you understand? So stacking fault energy is like a parent who is trying to bring the two partials together, who are repelling each other. So if the stacking fault energy value is high, joule per unit area value is high, the partials will be closer to each other. If the stacking fault energy per unit area value is low, then the repulsion will take them to relatively wider stacking fault. So think about these aspects. I will share the slides. I think today a lot of discussions we had. I will share the slide. Okay, tomorrow we will have class again. Okay, thank you. Okay.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Hang up.